Good morning. So we are starting today the lecture 32, and remember in the last lecture, just in the last lecture, we derived this expression for the drain current without, for deriving this equation we did not ignore the drain induced deep depletion, or the channel depletion. So we assumed that the channel depletion is occurring also due to an additional voltage potential which is induced by the drain bias, and that results in this expression of the current, which is more comprehensive than the simpler current equation derived earlier. This was simplified for small values of Vd to an expression like this, which looks similar to the one which we derived earlier, excepting for this term. Otherwise, the expression which we derived earlier was this first term minus half Vd square. Now there is a second term involved. This is of course for small values of Vd. For very small values of Vd, even this term can be neglected, and we get this, which is identical to the equation which we derived earlier. And therefore, the same expressions for GM linear and GD linear, which was derived earlier, will be valid. So GM, this thing linear, will be simply mu n Ci W by L into, with respect to Vg, therefore it is multiplied by Vd. Whereas GD linear with respect to Vd, so it is equal to mu n Ci W by L into Vg minus Vt. As discussed earlier, therefore, for very small values of Vd, the MOSFET behaves as a gate-controlled resistor or a gate-controlled conductor. A resistor whose resistance value or conductance value is directly proportional to mu n Ci W by L as well as Vg minus Vt. So by changing Vg, I can change the resistor value. This is called electronic control of a resistor. I can control electronically the value of a resistance using a MOSFET at a very low Vd value. So this is a very important thing. Sometimes, in varactor diode, electronically you can control the capacitance value, called electronic tuning. Similarly, here you get a device which is offering you a resistance whose value can be controlled electronically. Maybe you are designing an RC filter where the R has to be tuned little bit, R has to be changed little bit. You do it electronically. So replace the ordinary resistor by a MOSFET, bias it at a small Vd, change Vd slightly to adjust the value of the resistance. So this is giving you that advantage. At the end of the last lecture, I drew this diagram for the different conditions of MOSFET which prevail for all three cases, whichever we depicted here. Vg is more than Vt. That means inversion layer has been formed. But in the first diagram, Vd is either 0 or very small. The second diagram, Vd is equal to Vd sat. And the third diagram, Vd is more than Vd sat. Okay? You see the shape of the inversion layer. In the first case, you see the depletion layer was uniform. The width of the depletion layer was Dmax. This width of the depletion layer was Dmax. And you remember Dmax is equal to D for psi s is equal to twice phi f. Okay? That is very well. And then the green region indicates the inversion charge density. Maybe it's a plot of Qn versus length or distance along the channel. This may be Qn. And this is your Yn, Y. This is the origin. So you see that here in this case The inversion charge density is uniformly distributed over the channel, almost constant. As we apply now, go to the next case when Vd is equal to Vd sat. Then, as I told you, that this channel, which was earlier depleted to Dmax, okay, and there is no question of deep depletion because the inversion layer formed. That is why it was Dmax. You remember it very quite well. But then in this case, because now the inversion layer is formed and you have applied drain bias, a current is flowing, that results in an ohmic drop across the channel, along the channel, that the potential is will continuously vary from the source to drain, in this case from 0 volt to Vd. And this added potential, this is in addition to twice phi f, which was the maximum surface potential in the earlier case. So this added potential, which as a result, the potential at the surface becomes that twice phi f plus Vy varying from 0 to Vd along the channel. Because of that, the depletion layer will widen. And that is what we call some additional channel depletion due to the potential drop along the channel length due to the applied Vd or drain bias. And as a result, you know that the depletion layer will be slightly tapered out as indicated. May not be exactly linear, but some such thing. And the inversion layer will no longer be an uniform one. It will have maximum density at the surface. Gradually, because of Vy, at this point, ultimately, when Vd is equal to Vd sat, for which is equal to Vg minus Vt. I remember that Vd sat is equal to, from rough estimation, is equal to Vg minus Vt. Channel will be pinched off in this region. And that leads to current saturation. That means as we exceed Vd sat, we enter into the saturation region of the MOSFET, IV characteristics of the MOSFET. Okay? At this point, I told you, to the left of this, the resistance is very small compared to this. At this point, it is effectively 3 resistances in series. This is the R pinch off. This is the R channel, and this may be R drain. This R pinch off, PIPO stands for R pinch off, is very, very large compared to R channel as well as R drain. As a result, the voltage which you apply here, this is 0 and this is Vd. Practically the whole Vd will appear here. Across this, voltage will be roughly Vd. Because the current is small, the drop across these 2 resistors is very small compared to the drop across RPO. So over the pinch off region, a full voltage will appear. Over the pinch off region, the full voltage will appear. Practically the full voltage will appear. As a result, because the pinch off region has a very small thickness, the electric field in that region will be very high. Electric field is equal to the voltage divided by distance. So electric field over this region will be very high. So electric field in the pinch off region will be very high. So the drift velocity in the pinch off region will be nearly the V saturation. As a result, through the pinch off region, electrons will be compelled to move in a constant velocity, which is the saturation velocity in the medium. That means the carriers here will be hot carrier limited. And as a result, the velocity will be constant, and that leads to the saturation behavior. This is the second case, okay? When as you go to the next case, when VD further exceeds VD sat, you remember VD sat is roughly equal to, not exactly, detailed theory says it is slightly different, but roughly equal to VG minus VT. Okay? So when you consider, when you cross that value, when you apply a VD which is more than VD set, then what happens? This point of pinch off, this pinch off point shifts slightly to the left. This is your pinch off point. This pinch off point shifts slightly to the left. That means from this point to the drainage over this small delta L region, there will be no inversion layer formed. So let me repeat, when VD is more than VD sat, from this point to the edge of the depleted drain, no inversion layer. Practically, this will remain in subthreshold region. In fact, that is why we assume that in subthreshold Qn is equal to 0. That was my basic assumption. Now we assume, therefore, over this delta L, a very small region, what will happen? Over this small delta L region, there will be no inversion. This is called an extended pinch-off region. Therefore, this delta L, which was just 0 when VD is equal to VD sat, slightly increases with VD exceeding VD sat. And if your channel length L is comparable to that delta L, is not very, very large, then this will have some effect on ID. If your channel length is very large, so that delta L is small compared to that channel length L, then this delta L will have no effect on the drain current. But if delta L somehow comes to some value which is not negligible compared to L, then effectively the channel length will be reduced. You see, there will be an inversion charge density like this, and the effective cross section of this may remain the same, but the length is reduced. As a result, the channel conductance will increase, and hence within this region the carriers will move in saturation velocity. But over this region, the current must be continuous. The current entering and current entering here, that must be continuous. The current which is being sent from the channel, via the channel, and just entering this, the pinch-off region, will be increased because of the reduced length of the channel. And that results in a phenomenon which is when VD exceeds VD sat, then ID slightly increases, slightly. And that is what is known as channel length modulation, which is the case only for a shorter channel device, not a very long channel device.
What's the maximum depth of the layer?
Inversion layer depth is typically, in terms of values, it is about 100 angstrom. But can be
the maximum inversion layer depth.
No, everything, when things are very small, everything becomes dependent on every parameter. But for long channel, it is independent. For long channel, nothing will happen if VD is here in the source side when we apply a VD. In short channel, when you apply VD here, something will happen in the drain side. In fact, the barrier is reduced, and that is what is known as drain-induced barrier lowering. We shall be considering that after. DIBL is a short channel effect. Okay, so after this we discussed in the last class, and so let me once again tell you that when VD is very small, you remember ID is proportional to VD. But as VD starts increasing, but still remains on. That is relative. Then the nature of ID becomes something like this. We have found that it is something like some constant into VD minus some constant into VD square. Something like this. The second term is usually very small compared to the first. But this term becomes important when VD increases. That leads to, as a result, what will happen? The delta ID versus delta VD, which is equal to K1 minus twice K2 into VD. So the slope, which were for very small values of VD, this term was small compared to Q1. The slope was constant. But as we are increasing VD, because of the second term now dominant, and as a result, you remember, the delta ID VD, the slope of the curve decreases as VD increases. We say that we are entering into this. So if this is my curve, ID versus VD, this may be the point of saturation, VD saturation. So initially the curve is linear with a slope K1, but that slope starts deviating from that Q1 value, decreases, and we enter into a sublinear region. So the entire up to this point, from 0 to VD set, this region of ID versus VD characteristic is called linear region or triad region. But in the linear region, only at very small values of VD only, the ID VD slope is constant. Otherwise, it gradually decreases, and ultimately at this point, the slope becomes 0, because we assume that it is perfectly saturated. The slope gradually decreases to 0. Now at drain-induced pinch-off, you noted that QNL tends to 0. And you remember the expression of QNY derived earlier, that was derived earlier. I'm just reproducing. This is actually modulus sign. And as a result, putting YL, that means QNL, which tends to 0, means I have to write for YL, and VY becomes VD. So, therefore, QNL, the value of QN at the drain end, is equal to VG dash minus VD set, because that happens when VD is equal to VD set according to our the QN at drain pinch off I have told you earlier. and that is equal to 0 at pinch off. Solving this, we get an expression for VD set which is like this. Where and as before Vg dash is Vg minus VFB. So we now get a slightly more comprehensive expression for the VD set, which was earlier we just wrote as Vg minus Vt, isn't it? Vd set is equal to Vg minus Vt, but that was not a very correct and very accurate description because of the drain-induced channel depletion effect, which was ignored earlier, and the Vd set expression become more complex than before, but one can show that it is approximately equal to Vg minus Vt. In fact, Vd set can be, you can easily write down and compare, you'll find that is approximately equal to Vg minus Vt. But approximately. Earlier we are writing that is equal to, but now it is approximately equal to. Now substituting this VD-SAT equation into the ID expression which we derived earlier. We derived an expression for ID. Under this condition, which is more comprehensive, substitute for VD this VD-SAT. Substituting VD-SAT in the ID expression. We get an equation which looks like this. I will not, because otherwise the equation is very, very big equation. Let us ignore it. We get an equation which is something like this. M W by L mu n Ci into Vg minus Vt whole square. Looking very similar to the earlier derived equation. But here M is a function of doping Na, and it tends to half as Na becomes very small, tends to 0. If you substitute this expression for VD set in the ID equation, you get a comprehensive big equation, and finally can be expressed in this reduced form, where M is a very big one. It's a very big expression containing so many things, but most important parameter it contains is the doping concentration. So M we call a doping dependent parameter. Okay, and Na value goes to half, more or less, for small values of Na. That means when you are using a very low substrate, Na tends to 0 means for mathematically. Actually, when Na becomes small enough, say 10 to the 14, 15 in that range, this equation looks very similar to the earlier device. It tends to half, so it looks like to the very similar, the same equation which we derived earlier. So all these things, in doing all these modifications, etc., etc., making more comprehensive, we get equations which are not really that much very, very different from the ones derived earlier from simplistic assumptions. So sometimes what we want to say is this, that to look into a device first, never go into the most comprehensive picture. Always start with simplistic assumptions so that things can be derived easily. Get many physical information from those equations, try to interpret physically, think that whether this whatever happening from the equation, as the equation predicts, this should also happen physically or not. When these things are over, when you find you are satisfying, more or less satisfied with the mathematical derivations and with your physical expectation, then for achieving more and more accuracy, you bring in now other things and get to more For example, today people are not satisfied with any of these derivations, let me tell you, because MOSFETs are very complex in nature today, they are very small in size, so many effects come in, and as a result, the existing models, they can just predict, but they cannot predict means qualitatively predict, but they cannot accurately tell you that this should be the value. And for that, therefore, you need more accurate models. For example, nowadays people are solving all the equations numerically, because now I have to write down the equations in two-dimensional form, three-dimensional form, and a number of equations. We should solve Poisson's equation and continuity equation and current equation simultaneously. All these equations are written in two-dimensional form or three-dimensional form. Solving them analytically is not possible. You have to solve them numerically. And numerical solution is not an easy task. You have to satisfy the boundary conditions. Boundary conditions here are not the point boundary conditions, but boundary point conditions over plane, over surface. Things make very complicated. Fortunately, we have numerical techniques based on finite difference, finite element, and various other techniques. Using that, people have come up with more comprehensive models. But those models' problem is you can run it and get some values, but you can never think that if something comes which is erratic, you cannot explain it out. Because whenever you do some numerical model, there are many we are using computers, and computers cannot handle certain situations which human being can handle. When things go to infinity, human being can stop somewhere. But computer, if it is not instructed properly, it will go on running and running and running. So some problems arise in computer. People truncate the errors. We just try to minimize the error, and as a result, we sometimes get some erroneous results which can never, unless you know the whole physics of it. Therefore, our approach is always in device physics today, though it is very complicated now. I have to understand always from the simplest model, one-dimensional, this assumption, that assumption, gradually increasing the accuracy and coming to a more comprehensive. So please keep it in mind, and that will be helpful. Those will be going to the VLSI, a very good VLSI design, where things too much dependent on the back end, that means this device physics, technology and other things. These things have to be kept in mind. Okay, now consider another very important aspect called body effect. Also called substrate bias effect. So far we have assumed, though we have shown separately the substrate potential, but we have assumed in all derivations, we have assumed that Vs is equal to 0 and Vb, or also we have written it as V substrate, that is equal to 0. That means we assume source and substrate shorted and grounded. This is the assumptions made so far. Now, normally the substrate source junction should not be forward biased. If I forward bias the junction unnecessary because you are not really gaining anything. By substrate source junction forwarding, you are unnecessarily wasting power and there will be no gain nowhere in the transistor operation. So never substrate bias is forward, but substrate bias, source substrate is maybe reverse biased. Never forward bias. This is very important. In fact, if VBS means the source, the bias at this base, B stands for body. B stands for body, and otherwise body and substrate are the same. VBS means the bias at the body with respect to the substrate. For, you know that for our NMOS, what is the polarity of VBS for reverse biasing that junction? VB potential at B with respect to source. It should be negative. P should be negative for reverse biasing. But for simplicity, we shall assume that this VBS, or we can put a modulus sign, does not matter. But we will always assume that when VBS is positive for reverse bias, because we are never considering any reverse bias situation. So VBS, as you increase the VBS, we shall see that effectively the threshold voltage also increases. VBS under reverse bias condition, if it is increased in magnitude, the threshold voltage also increases. That means we can have a additional tool for the control of threshold voltage electronically. I want to adjust the value of the threshold voltage to adjust the IV characteristic of a transistor. I can apply a reverse bias at the substrate. It has its bad effect. Usually effects are bad, let me tell you. But it has its good effect also. Good effect is the electronic control of the threshold voltage. That is a good effect. Otherwise, it is not a very desirable effect. If you draw the surface potential diagram along the channel, then you remember that this is a case when VD is equal to VS and maybe equal to 0. And you remember, then this is nothing but VBI. This I have plotted for VG dashed equal to 0. That is under flat band condition. Under flat band condition. And also it assumes that VBS is equal to 0. That means short substrate shorted and grounded. BS0, VBS0 means short substrate shorted and grounded. Now if you apply a substrate bias, what is going to happen? Other conditions remaining the same. So this is the curve for VG dash is equal to 0, but VBS is not equal to 0. So that this one becomes VBI plus VBS. the barrier, because now it is junction, as I told you, there's both source, this is Vs, and this is Vd equal to Vs, and that is equal to 0. So this is all 0 volt line, and this is something negative. So this is minus Vbi plus Vbs, and this is minus Vbi. This line is minus Vbi with respect to this to be 0, and this line is minus Vbi plus Vbs. So what has happened as a result? You see that when we first, let us assume that both source and drain are grounded. Vg dash is equal to 0 means Vg is equal to VFB. Vg dash is equal to 0 means Vg is equal to VFB. The flat band condition prevails. So that the potential barrier at the source and drain end will be Vbi corresponding to the surface. Now when you apply a VBS, a reverse bias between the drain and the substrate, between the source and the substrate, it is automatically between the drain or the substrate also, because both are grounded in this particular case. So this reverse bias is automatically between the drain and substrate as well as between the source and the substrate. So what is going to happen? This whole thing will go down. Effective potential barrier will now rise to VBI plus VBS. Now suppose I want to make this device on. For turning the device on, what has to be done? I have to apply a small Vd at least, because current has to flow. Otherwise, if Vd and Vc both remains 0, current will not flow. I can create an inversion layer, but current will not flow. Either you try to produce an inversion layer without current flow, then you maintain the condition, or you produce an inversion layer also have a current flow. In that case, what has to do? You have to apply some Vd, and you have to raise that Vg dash from 0 to above. Where above? It should be more than Vt. Equal to or more than Vt. You remember that. So what you did earlier, you remember? For when you apply Vg dash is equal to Vt, then the surface potential, this thing becomes Vbi minus twice phi f, because surface potential saturates to twice phi f at the source end. So this thing goes up, and this barrier is reduced from Vbi value to Vbi minus twice phi f. Electrons will be injected from here, and if the same condition prevails, Vd is equal to 0, electrons will be injected from the drain also. So there will be a strong inversion layer uniform produced over the channel. But now if I have a Vd here, you are extracting those electrons. Instead of supplying electrons from the drain, you are extracting those electrons, and there is a field, a current will flow. Because of that, there will be a potential drop, and hence a drain, drift induced current will flow, which you have derived earlier. Now this is true for VBS is equal to 0, which is the case we have dealt with so far. But suppose VBS is non-zero, VBS is a reverse bias, then do you expect the same thing will happen with VGS with the same VT? That means, suppose our VT was 3 volt. Now when you make VT means VG dash minus VG minus VFB is equal to 3 volt. VT minus 3FB. Normally we assume VFB is equal to 0 for all things. Please remember. So when I said 3 volt, I am assuming VFB is equal to 0 volt. Okay. So when suppose VT is 3 volt, then when you make VG is equal to 3 volt or more than 3 volt, the inversion layer is formed in the first case. In the first case, when VBS is 0. In the second case, when VBS is non-zero, a reverse bias, do you think for the same 3 volt or slightly more than 3 volt, the inversion layer will form? No, because you know that when you apply VT, then what is going to happen? Because of this VBS, the potential barrier remains as VBI minus twice phi f plus VBS. because plus VBS is always there. To cause sufficient injection from here to here, I have to apply much higher Vg than before. To have the same amount of inversion layer to be formed, maybe I have to apply a Vt which is 5 volt, which I have to apply Vg which is 5 volt. Then my threshold voltage is 5 volt. But I want to say that simply by applying a reverse bias at the source, you can increase the value of the threshold voltage. And to have a quantitative derivation of all these things, let us not go into the complicated one. You see that you remember the expression for Vt minus VFB. That was equal to 1 upon Ci root over twice Q Na psi s twice phi f. Okay, that is with VBS equal to 0. Standard expression. Vt is equal to VFB plus this. But then Vt minus VFB with VBS not equal to 0 is going to be 1 upon Ci twice Qna epsilon s. And this thing effectively becomes now twice phi f plus VBS. I am assuming VBS positive for reverse bias. Plus twice phi f. Then you can write for Vt, delta Vt, which is the change of threshold voltage with VBS minus without VBS. And that is simply equal to I am putting a sign also, sorry. Let us put the modulus sign, there's no harm. Why I have not put here twice phi f plus VBS? You please judge and tell me afterward. You see that within the square root sign, which is nothing but the charge density QD, I have put for psi s twice phi f plus VBS. But then for psi s, it is this plus psi s also saturates to phi s. But here, the outside, we are not putting that VBS. Why? Please try to verify this and tell me afterward. Okay? Those mathematics I had intentionally avoided. So main thing is, even if it is there, does not matter. In fact, but it is not there. It will not be this twice phi twice. Here, for example, this VBS will not appear. So this delta Vt expression is given by this. So it predicts from here you can easily find out what will be the change of threshold voltage. we are so much bothered about this thing? Because you know that the threshold voltage is a very important parameter of a MOSFET like beta of a paratransistor. For a MOSFET, VT is a very important parameter. VT controls everything, everything. Most of the other parameters of the transistor, MOSFET. And with reverse bias at this substrate, you see that VT changes. And therefore, the current voltage characteristics changes, everything changes. So reverse bias at the substrate has a profound effect on the entire behavior of the MOSFET. This should be kept in mind. And in general, seeing this, you see that the delta VT, the increase of threshold voltage as a function of VBS, you can say it's proportional to, you can square root of VBS if you plot, because after all there is a square root sign. For large values of VBS, this term is small compared to this term is large, so everything it will be proportional. Practically delta VT will be proportional to square root of VBS. For large values of VBS, delta VT is proportional to the square root. So the curves is expected to be something like this, let me tell you. And here, of course, the parameter which I varied is this parameter, square root of epsilon s Na divided by Ci. You just see the equation. The slope of this curve is this. So where square root of Q Na by Ci is a very important, because otherwise epsilon s is a constant. Constant, but you can vary the for different semiconductors to, that is why I have given. Otherwise, most important is Na, the doping concentration of the substrate, and Ci. Ci is equal to epsilon I by Di. So it is proportional, Di goes up. So if I want to reduce the effect of substrate body effect, so what has to be done? To reduce the body effect, I have to use a smaller Na, a lower doping concentration, okay, and a larger thickness of the insulator. Can you tell me why? You see from here the delta Vt is stronger, that is the effect of body effect. Body effect is stronger when doping concentration of the substrate is high and when the capacitor, insulator capacitance is less. That means the thickness of the thing is high, thickness of the dielectric is high. Can you tell me why? First thing is Ci, smaller is the value of Ci, means the, yeah, and what about Na? Na means actually if I have a large Na, the VBI value is large. Higher is the value of the dopant concentration, VBI value is large. And less insensitive with the delta Vt effect, the body effect as a result. So these are the two things which you can little bit play upon. Otherwise, your devices are totally, that under the influence of the body effect. And this body effect normally arises in an inverter. I will just discuss. So to reduce the body effect, Now, can you tell me that we shall discuss afterward, but can you tell me that in this inverter configuration, this is called driver and this is called load. Okay? Which transistor will be affected of the two, driver and load? Which one of them will be affected by the body effect? Load. Very clear. Because it is this is the source of the load, it is the drain of the load. The source of the driver, drain of the source and substrate both are grounded. In the case of driver, the body effect does not arise. On the other hand, for the load, this potential is changing from practically 0 volt to V naught or VDD minus VT. The VO is varying from almost 0 volt to either VDD or VDD minus VT. When it will rise